just again remind you that you've seen this before. You know from last lesson, you know from last term, that if you multiply two complex numbers in polar form, you multiply the moduluses, you add the arguments, and that works all the time. If you divide the moduluses and you subtract the arguments, but that is not specifically de Moivre's theorem, even though it works the same way as de Moivre's theorem. De Moivre's theorem is a power-based theorem. So this is the official de Moivre's theorem. If you've got asked on, like, on your external exam, it might come up with a reference to Moivre's theorem and ask you to do something with it. That's de Moivre's theorem. The stuff above with multiplication division isn't officially de Moivre's theorem, even though the principle is exactly the same. So de Moivre's theorem states, and it's just to follow on from this multiplication rule here, that if we have a complex number to the power of n in polar form, well, that's just equal to the modulus to the power of n multiplied by kiss of n times theta. And so we just add theta together n times, get n theta. And that's it. So with that in mind, I'm going to throw at you, and I know a couple of people are writing things down, so I'm just going to go to there. I'm going to throw at you a couple of quick examples. And I do this very wary of the fact, and I wish I had put a harder example on here now and I didn't, but you'll see them in your textbook. Last term, you had an exam where I put down a complex, unfamiliar example of this that had 3 terms in it. So it looked a bit like example 2 with a function, a term on top, 2 terms on the bottom. You had to convert them into polar form, and a lot of you got it wrong and just made mistakes in it. So I want you to get this right. This is procedural stuff that you can just work through and get right. So example 5 on this particular OneNote is cis pi on 3 cubed times 2 cis pi on 6 to the power of 4. And this simplifies to give cis 3 pi on 3 times by 2 to the power of 4 cis 4 pi on 6. And that's equal to, and I'm going to leave this the same, but I'll simplify that down to be cis pi. That can be simplified quite nicely, but I don't want to do that simplification yet because I want to do this multiplication first. This is 16 cis 2 pi on 3. And that multiplication works using our initial rule. It becomes 16 cis pi plus 2 pi on 3, which is 16 cis 5 pi on 3. And of course, technically, we're done. Because the question hasn't asked us to put it into Argand or Cartesian form, and we were given it in polar form, so we'd be very comfortable leaving it in polar form. If you needed to put it back into Cartesian form, though, you'd obviously expand this out to be 16 cos 5 pi on 3, which is an exact value, plus 16 I sine 5 pi on 3, and just evaluate those. Any questions on that one? That's a simple example. That could come up as a simple familiar question in either your Unit 3 exam or the external exam. And if it did, you need to get yourself into a place that you're happy to see a question like that. If you get a 3 or 4 mark question like that, that's a good place to be. You want that question. Term to simplify this is a pretty simple example, but it could come up as a complex familiar question. There are multiple processes involved here. Not least of all, you have to convert those into polar form. Now, this is not even an outlandish example. You could just do this expansion. Multiply that by that by that, and then just divide by this. You could probably do that, but it's still going to take a whole page of working just to do that simplification. Whereas de Moivre's theorem will take us probably 2 lines to turn them both into polar form, so 4 lines in total there, and another 2 or 3 lines. So it's still quicker in the end. But we do get some not as nice numbers. So first of all, I want to calculate what 3 plus 4i is equal to in polar form. And I get my r value is equal to the square root of 3 squared plus 4 squared. And so that's equal to 5, because I've seen that one before. And my argument is equal to tan inverse of 4 over 3. But I'll just make sure that I'm quadrant aware. And then I have to worry about marking out anything else. 3, 4 is up here. So I'm expecting an argument that's in the first quadrant. And when I do this, I should get an argument that's in the first quadrant. And if I do that quickly, on here, I get tan inverse, I'm in degrees, and this hasn't really specified what I have to be in, so I'm happy to stay in degrees. 53.13 degrees. My second one, 1 plus I, R is equal to the square root of 1 squared plus 1 squared. Show me at least one line of working, and that's the square root of 2. Theta is equal to tan inverse of 1 over 1, and tan inverse of 1 is 45. Again, they're both positive, so I'm expecting this to be at 1, 1, which is here. It's in a positive quadrant, and I get it in a positive quadrant, so I'm happy with that. And now I've got this as my calculation. I need to calculate 5 cis 53.13, that's pretty poorly written, I might just zoom in a bit there, over root 2 cis 45, and that simplification happens like this. It's 5 over root 2 times cis 53.13 minus 45. We subtract those. 5 over root 2, I multiply top and bottom by root 2 to rationalise my denominator. Sorry? Oh, it is 2. Yeah, sorry, you're right. That's cubed. Ignore me. 125 cis 159.4 degrees over root 2 cis 45. Now I write down my next line. 125 over root 2 cis, and I get 159.4 minus 45 in between working. And 125 over root 2, I multiply top and bottom by root 2 to rationalise my denominator, and I get 125 over 2, which is 62.5 root 2 cis 114.4. Now, at this stage though, I might convert this back into Cartesian form. And you might not need to do this, but we started in Cartesian form, so I'm going to convert it back. 62.5 root 2 cos of 114.4 minus, and by minus I mean plus, 62.5 root 2 I sine 114.4. Now, if you just take a second here, and I just shoot up here very quickly to the start, if I expanded this and did all the simplification, the expansion of that is going to give me some large numbers, but it's going to give me whole numbers. When I divide by this, I'll have to multiply by the complex conjugate. It will work. I may end up with a fraction. I'll probably end up with a divided by 2. I don't think I'll end up with any thirds even. So I'm actually expecting, even though I've got a not as nice angle down here, I'm expecting my answers to be whole numbers or maybe halves. But I have rounded. So I'm expecting my answers to be not quite whole numbers or halves. I have kept my answer on the calculator though, so I'm hoping that's what will come out. And if you haven't kept your answer in the calculator, you're probably going to get something really close, and then you can do that rounding and pretty confident that's what it should have been. So I'm going to subtract 45 from that, and then I'm going to calculate 62.5 times root 2 times cos of my answer, and I actually get, oops, that moved on me, negative 36.5. Then I'm going to change that to be sine of my answer, and I get plus 80.5 pi. That worked out quite nice. Any questions on that? So if you just keep that in mind, if you're given your values as nice whole numbers, but in Cartesian form, and you convert to polar form and numbers end up being horrible, realistically, at the end of the question, the numbers should go back to being quite nice. Maybe with some surge involved, depending on where you're up to. So in this case, I've come out with something quite nice. I'm pretty happy with that. And that's me. Any questions? How do I do what, sir? Oh, that's a good question.